This is my Warco WM250V 3-phase infinitely variable lathe. Came with a 3-jaw chuck, 4-jaw and a faceplate, and I absolutely love it. But could it be improved? I was going to say that. Welcome back to the workshop. So this is my Warco WM250V lathe, and I absolutely love it. Now, quite a few years ago I was looking to buy a lathe. I wasn't sure if I really needed it, what I was going to make. I had my CNC router and I had my drill press. A friend of mine, who unfortunately is no longer with us, he said, well look, the holy trinity of a workshop is a drill press, a milling machine and a lathe, and between those three you can make bits for the other one and you can kind of make everything more or less. And he's absolutely right. I've made all sorts of things on this. You've probably followed the channel and seen me make things for the electric go-kart, things for the drill press upgrade, and for my CNC milling machine. So yeah, I really wouldn't be without this. It's a fantastic machine to have. So in terms of what you can do with it, you can swing apart maybe about 120 millimeters, just under 5 inches. It's not a gap bed lathe, so that's your limit. Even if you could put something larger on here, you're going to be really limited by torque, even on this with the inverter drive. But you know, it's a fairly decent sized part, and you can certainly make a lot of things from that. In terms of distance, I forget what the manual quotes, but if you imagine there was a live center in there, you're talking about 450, maybe 500 millimeters, give or take. So what's that? Circa 18 inch, something around there. So, you know, it's a really good size for a hobby machine, and yeah, been really pleased with the things you can do with it and make with it. So this is the V model, which I think stands for the variable speed. Now you can vary speeds with a range of different approaches or technologies. This is the inverter one. I think it was a branded Delta drive, if I remember right. I'll put the pictures up of when I installed it. And then you've got the variable speed down here, which is a potentiometer that goes into the inverter, and then it's a 3-phase motor that then runs the spindle. Plenty of power, plenty of torque, nice controllability. Another way that this can be done, I think, is a DC control system. That's a different version of the DC motor. I've read some mixed reviews on that kind of approach, so I'm a big fan of the inverter technology, so I went for this V. The other options are, I think there's 2 more options you can have. There's a belt drive. They do a belt drive model. Trouble with that is you're fixed on a certain speed, and whenever you want to change that speed, you've got to change the belts over, which I think is a bit of a pain. And then the other type of lathe, although you probably have to get a little bit bigger than this to get that, would be one with a gearbox where you've got levers and you can select your speeds that way. I think this is a great sort of approach for a hobby size lathe, not too expensive, variable speed, inverter, 3-phase motor. Certainly seems to be I think that's my recommendation anyway for that type of speed control. So like most lathes, you've got power feed as well on your traverse for your normal cuts, but because you've got this 4-way system here, you can also engage power feed on the cross slide here, which can be useful if you're facing off and you want a nice finish, for example. The tailstock works really well. You've got a lever back here on a sort of cam, so you haven't got to fiddle around with a wrench or a spanner here every time you want to lock it off, so that's quite nice. I did have some problems, and I'll put a link to the video, where it stopped ejecting the tool, and what had happened was the thread had got damaged at the back here. There's a tiny little grub screw that was just engaging in the nut. I fixed that and it's been great since, so apart from that I've been trouble free with it really. So up here you've got your main start stop, so on off. You also got forward reverse, and I don't know why, but there's a 0 in the middle that doesn't do anything. And then you've got an emergency stop up there. Also down here you've got these 2 knobs. This one controls the direction of feed, that's on this lead screw here, and you've got speeds A, B, C. And if you look up on this chart here, you've got the A, B, C's here. Depending on the ratios you've got, and we'll come on to that in a bit, you've got different feeds there on your traverse. So in terms of standard kit, you get this 3-jaw chuck. This is made by Fueda, I think. Been very impressed with that, no problem. Obviously, if you take the part out, you do get a slight misalignment, typical with a 3-jaw like this. But they also supplied a 4-jaw. Obviously you can dial that part completely concentric, and I've not used it, but there's also a big faceplate that would go on the back here as well if you've got very awkward parts that you want to machine as well. So pretty comprehensive set of parts that came with it. Just while we're talking about chucks, it can be a little awkward, or it takes a little bit of time to swap them over between the 3 and the 4-jaw. You can't get the nut fully off, so you've got to loosen them off quite a fair way, then push it off the seat off here where it engages, and then that moves the thread away, and then you can get the nuts out. So it's a little bit of a two-stage process, and the reverse when you're putting it back together. But you know, it's okay. The biggest problem is whenever you walk up to a lathe, it's always got the wrong chuck on. If you want a 3-jaw, it'll have the 4-jaw on. If you want a 4-jaw, it'll have the 3. But you know, these are the things you find when you own a lathe. The other thing I looked for when I bought this lathe was to get the largest bore possible. Now I'll put the number on the screen. I think it was somewhere in the 22-25mm range. And obviously the larger the bore you've got through here, the bigger piece you can machine or push through just to machine the ends. So that's pretty handy if you're doing ball screws or anything that gets particularly large. So it's certainly worth looking out for the size of the bore in any lathe you're considering buying. Okay, so what's this project about? Well, I'm sure future me has put some kind of thumbnail, some kind of descriptive title, and we know we're going to add an electronic lead screw to this. So let's just talk briefly about why. The relationship between this and this lead screw is determined by the number of change gears that are at the side here, and those have to be configured so you cut the correct lathe, because when you engage that half nut and you're machining that thread, obviously the ratio between this and the rate that it's cutting that determines your pitch, and you don't want to get that wrong. And to vary those, you then end up changing all these change gears out, and there's some kind of banjo system on the back here. And basically, well, it tends to take me about half an hour to change them over, get them all dialed in, because you adjust the backlash with a bit of paper and get them all sounding nice and running true. And then when you're done, you swap it all back again. So luckily, people have been here before and thought about this, and there are all sorts of electronic lead screws available, commercial ones. There's one in particular from James Clough, Clough42, that caught my eye, and it's been on my list for some time, so let's get to it. Before we go there, there's two more things I want to talk about. So when I bought this lathe, I knew I wanted digital readouts, so I ordered them at the same time. So I bought the display, and I bought the Z and the X read heads, and then I had to, make little bits and pieces to adapt it to get it to fit. And I really wouldn't be without it. I much prefer that than using the hand dials. I think that's been an excellent modification. The other one is, again from day one, I wanted to use the quick change tool post. So I bought this. There's a bit of machining involved that Warco did to adapt it, but that wasn't too much extra. And then you can just drop tools on. Now in theory you can hook them up to a library tool, 1, 2, 3, 4, that kind of thing, and then when you drop them in, you're pretty close to an original position, hold a reasonably tight tolerance. In practice, I'm only making one off, so I don't do that, but it's really nice and quick. Just drop tools in, they're on center height, and away you go. So I find that a really useful addition. Now I'm going to turn it on now, and it'll start to make a little bit of noise because the 3-phase motor at the back there from the inverter, it's also got a mains industrial sort of big fan at the back of it that provides cooling all the time, and that's on all the time, so it runs every time the lathe is on. It's not temperature controlled or anything like that. It makes a little bit of noise, so I tend to turn it off for filming, but I need to turn it on now because I want to show you something else that kind of annoys me about change gears as well. Okay, so there it is switched on now. You can hear the fan noise at the back. It's not excessive, but certainly worth it to have the inverter. Right, so the thing I want to show you is, we'll do these jaws up first. So I'm going to spin it. I guess it could fit apart as well, but let's make sure we're not locked, and we'll start it up. Okay, so running about 650 RPM. I mean, it doesn't really matter, you can dial in all sorts of speeds. It's pretty responsive. But if you, I don't know if it's coming across on the audio, but if you listen, you can hear the kind of rattling noise. And that is the slave gears on the banjo that are just jiggling around and making a noise. And I don't think it sounds very premium, very quality. Nothing against this lathe, they all do this, but if we can get rid of those gears on that banjo set and have an electronic lead screw, this will sound really sweet. Let me show you what I mean. Okay, I've just switched the power off because we're going to go into the end here. These are nice quality thumb screws, or thumb nuts, I suppose. So we've got the cover off now, and you can see how it all works. So we've got our motor down there, drives this pulley here, and that's driving the spindle, so that's in like high range. You can drop it down to a low range. There's another belt there that goes onto this large pulley, and then there's a small pulley here that would come up to here, and that's a low range. I've never used that actually. I think that's what they call range A, and we're currently in range B. So we can go up to 2,200 RPM like this. If we configure it the other way, we can go up to 400, but we get an awful lot more torque. So I guess you had some really large pieces, but as I say, I've never had to use that. Then the other things you can see in here, yeah, we've got our safety interlock there, there's a little idler there, and then these are the change gears, and they live on this device here, which I'll show you in a moment, called the banjo, and that basically brings the speed from here through these series of gears to this shaft here, which is the shaft that controls your traverse when you're cutting the threads. So that's determining the ratio to set your thread pitch, and you have to mess around with these, and it's a real pain in the butt. So another thing you can see here is a proximity sensor that's picking up on these little studs. I think there's 4 of them per RPM, just give it a little bit more accuracy or resolution. And then that feeds across to this display here, so you can see your speed. Now on the electronic lead screw that James has developed, it had that speed detection built in, because you're going to end up putting an encoder on here. So I'll decide if I keep that or not, because one of the things I'm thinking about is maybe mounting the control box here. But yeah, I've got options. I need to look into exactly how I'm going to do all this. But anyway, yeah, we've got the speed sensor there. So what I'm going to do here is just loosen this bolt off down here, and then carefully just move it out of engagement. In fact, I'll bring it all the way around just so you can see it, in case you've not seen all these before. This is the carrier system that all the gears sit on, and they've got these little clips on here, and the spacer washers, and the washers are all different from each other, though they look almost the same. It turns out to be a bit of a pain to get this configured, in my experience anyway. So yeah, I won't be sad to see that go. So what we'll do, I'm just going to bring it out of engagement so it's not touching, and hopefully we can get the lid back on. It might not let us, I don't know, but let's see. Get it as close as we can. Okay, so I've got the end cover back on again. We'll fire it up, get about the same RPM, and we can have a listen. I'll just start it slow, just in case something's fouling. And then we'll go up to, I think it's about 700 RPM. I don't know if that's coming across, so we'll flick between this. So this is no lead screw gears engaged, and then this one is with those gears engaged, driving the feed screw down here. Try some higher RPM. That just sounds really sweet, really nice. So there's 2 benefits to that. One is we don't have to change all those change gears every time we want to cut a thread. Infinitely variable number of pitches and etc. Metric, imperial, everything. Nice and easy to change over. The other advantage is that second one there will sound an awful lot sweeter. I haven't got the gears rattling away. Does that matter? Not really, it still functions, it's not a problem, but Maybe it's just me, I don't know. I just like that sweet sound of machinery. I know, it's working, you're listening to it, and it's telling you whether it's happy or not. When it makes happy sounds and it's nice and smooth, I think it's always a good thing to hear. It does remind me of, going back a few years now, when I first met my wife, I bought her a sewing machine, because she's into sewing and things like that, of course. And I didn't know, actually it wasn't a sewing machine, it was an overlocker. So if you're watching this in the States, I think you call it a serger. But when you're sewing clothes together, yeah, sewing machine, I'm sure we've all seen those, it just puts some threads down. But an overlocker or a serger, it rolls the edges together and it gives you a sort of stitched edge that doesn't come undone. So it's used on t-shirts and all sorts of things like that. Anyway, as you can tell, I knew even less about those than sewing machines. So to surprise her, I went into the sewing machine shop and I said, she wants this overlocker. I don't know much about them. Tell you what, can you just show me them running? I want to have a listen. So a guy in there, he plugged about 4 or 5 of them in and he just ran them through their paces. And I said, it's that one there, no doubt, it's that one there. And he says, you've chosen a Bernina, and it was made in Switzerland, or it might be in Japan, I can't remember. I think they've made them in 2 places, which I then turned out, then realised afterwards, once I got it back to my wife, she was delighted. It ran beautifully smooth, and it's lasted years and years and years. She serviced it and so on, but it's ran really well. The point is that I bought it just based on what it sounded like, because it sounded nice, and therefore it was probably going to last a long time. So, long story there, but that's kind of another benefit of doing this as well, and something I really want to do on this lathe. So, let's go and have a look and see what's actually involved in this project. So this isn't the actual final version of all the bits I'm going to use, but it just gives you some idea about how it's all going to go together. So these are kind of some old things I've had off old CNC machines and so on. So what we'll do, we'll unpack this. It's got the main control unit, the display unit and the encoder, and just try and lay it out on the bench. Just give you a bit of an idea about how it all goes back together, and also to remind me, because it's a while since I looked at this project, which we'll get into in a minute. Right, let's start pulling some of these bits out. So the first box we'll pull out here was the one that I ordered from James's eBay site, so Clough42. I went for the combination kit, so we've got the display at the front here, and then there's like the interface panel there. And I think I ordered this stuff back in, so we're shooting this in about somewhere in September 2022. I ordered this stuff around January, February time, so I've had it quite a while. I'll tell you why in a moment. So I just need to remind myself what I've actually got in here. Yes, I remember now. So remember opening it up and you get the nice label in there, nice box, well presented, just gives you that nice impression that someone's thought about it. All the little header connectors I need to solder on. So we've got the little board, hopefully you can see that in there. And then this is a generic eBay display or sort of interface board where you can do lots of different things with. But it came with this kit, and it just, may as well just order it all together. And then these are the parts that James has 3D printed, the sort of spacer. He's got lots of videos on how he iterated to get to this, so it looks really nice. So I decided to go for that. And little 3D printed buttons as well, and some hardware. So that's nice. So we'll put that back in there, just so we don't lose it all. In fact, what we'll do, we'll just keep this piece out, because that'll help explain where it goes in the scheme of things. So put that to one side. Next thing I've got in here is, I think I ordered it separately, but I put it all in this same box, this DigiKey box. But this was the encoder that he recommended. So there are certain requirements you need to have in terms of the type, pulses per rev, quadrature and so on. So that came with, sorry it's out of shot, hold on. Here we go. So this is the model I went with, which is the one he recommended. We definitely needed the 1024 pulses per rev, the voltage range, and there was something else about it as well. So this is the model I went for. As you can see on there as well. And then You've got all these wires at the end. I'm sure it'll all become clear exactly what I need to put where. And essentially this is then sensing the speed of the spindle of the lathe. So you independently control the lathe speed. This detects the speed you're running at on the main spindle, and then it's got to convert that to work out how to run the lead screw. So that's part of the system that we need as well. Okay, next we'll have a look at the microprocessor. So I think in the end I ordered this direct from Texas Instruments. So here it is. This is the model number that you need. Apparently quite a powerful processor. I don't know a huge amount about these, but this is the one that James recommended and developed his kit around. So let's have a look at that. And so if we open this up, so technically it is an evaluation kit, so you come with two parts of the board. One's the main processor and one's the debugging side, and I guess the idea is once you're happy with that, you port it across onto something cheap and small. But you know, in the scheme of things, this actually is not that expensive, so I think that's why James just went, yeah, just stay with this and use it for the main project. Why not? And then here is the actual board. I'll leave it in the bag for now, the static bag. But you've got, I don't know if you can just see the main microprocessor down there, loads of inputs and outputs, a whole stack of things it can do. You could do all sorts of things with that. And then there was something else I wanted. Oh yeah, here we go. So it's a generic device here. I can use it for all sorts of different things. So I'm not expecting you to read all that necessarily, but yeah, you got all the pins labelled up what they do there. So quite a nice bit of kit. So that's the brains of it. So I'll put that in there. And obviously we've got to use that information to drive the lead screw. So this will interface with, I've just got this old, really old analog microstepper driver. I'm just going to use this for just illustrating how it's going to go together. I don't think I'm going to use that in the end because that only drives steppers, and I'm sort of tempted to put a servo on this just for the noise, if nothing else. And I think that's what James went with as well. Anyway, just for the purposes of showing how it's going to lay out, we've got that there, and then that obviously then gets connected into some kind of stepper or servo, something to move the lead screw anyway. So that will go into these ones here. Now this is a very old one off a very old CNC machine. I think it's a pretty low torque, might be 1.7 Newton meters, can't quite remember. So yeah, I don't think that's really going to be suitable, but just to illustrate what we're trying to do here, let's put that in there like that. Then we need a few other things. So this I think needs 5 volts, and James used one of those, what they like to call over there, a wall wart. So plug-in adapter like this. Now this is one off my label printer, and what I'm actually probably going to end up using in the end to provide the 5 volts to the, I think we need to provide some power to this, but we certainly need to provide it to this as well. I'll probably just use one of those DIN rail mounted, because I'm going to make an electronic enclosure, so I'll probably do a 5 volt DIN rail mounted power supply instead of using this, but gives you the idea that we need that power. And then we also, this is only getting signals so far, so we need power to drive that, and I'll probably end up using something like this, although this one's only up to 30 volts, which I think is a little on the low side. Again, this is out on a very old early CNC project that I made, and then that will feed into the power, which is down here. And yeah, so just to make it a little bit more obvious, that's obviously got to go into there. Let's put a wire across there. There needs to be a signal going out from there into there. And I was thinking about this actually. This has got 5 volt supply, which I'd initially assumed is what you needed this for, but actually the little display kit here, I can't remember now, it came with somewhere in there, oh yeah, I don't know if you can see it through the packet, but a little power supply, and that I do vaguely remember had to get soldered onto here. So this little display unit here, which feeds into there, definitely needs the 5 volts. Now whether that then when it connects to this, let's put that wire on, indicating that they're going to talk to each other as well. Maybe the 5 volts gets fed there, or maybe this needs to be split and there's a 5 volts feed into here. Either way, I'll work it out, but I think essentially that's what we've got. So we've got the main brains of the unit in here, the microprocessor, getting its signals from the encoder that runs off the main spindle, so it knows where it is and the speed that's running at. Then depending on how you set this, or which thread pitch you're after, metric, imperial, whatever it is, it feeds signals down here. It goes into this stepper motor driver in my case. That's run off the main power supply, so it can put power to the motor and tell it how to move, and that joins to the lead screw. So these two are synchronized, and then the human interface is over here, and that's where you tell it what threads you want and so on, and that interfaces to this main board. And the bit I've just got to work out then is if they both need power, or if this is going to get surrogate power off here. But I think essentially that's the layout and the principles of how I think it all works. Oh, hold on, I cheated a little bit. I read the manual. Well, when I say read the manual, I went back and watched the original videos from James from 3 years ago, so I haven't watched them for quite a while. And actually how this works in terms of the power is this little interface board here. You solder on a little plug-in jack connector for the 5 volts. This has got these little terminals down here that allow you to plug it on like a daughter board, so that sits on top of there. So that 5 volts goes into the board on top, and then it's got a 5 volt 3 volt converter, and that will power the board underneath. So that is the only power you need, just the 5 volts, and it will convert that to the board for the DSP. And then the display is just separate over here. Right, yeah. Cheating slightly, I know, reading the instructions, but that is actually what I need to do. Now, James did a great series on this about how to develop it. He did a lot of R&D, and he looked in depth at the different servos and stepper combinations, and he's got lots of graphs, and he measured the torque, and I thought that was really interesting and really useful bit of information. He ended up using, instead of a stepper, I think it was a servo with this board integrated, that sort of size. Nice thing about that is, yeah, it's all compact. You don't have this separate piece, so you just put power and signals to it. Being a servo, plenty of power. You do have to tune it, so there's a little bit of a tuning loop to go through. But once it's running, again, it will, coming back to that sound again, you won't have that stepper judder and the stepper, you know, the kind of sound that kind of creates. A servo is going to be a lot smoother. So I may go that way. I looked into the cost, and it's not too bad for that actual unit, and James has had great success with it, so I'll probably go that way. But anyway, just shows you the schematic of roughly how it's laid out and what does what. So I just looked at all the electrical pieces we need. I thought we'll strip some of this down and have a look at where it's all going to go, so I can make or plan ahead at least for adapter brackets and where I want things. I've taken the cover off. I have put the safety interlock in there, that's the other part that comes on the cover, which basically means I can run this without the cover on. Obviously there's a risk involved. This thing will take your fingers off, no problem, but I will need to run it at least a little bit while I'm trying to work out what goes where and test it all out and make sure it's running. So I have decided I've overridden the safety feature on that. You'd have to make your own calls on that, but obviously this is a very dangerous bit of kit now. So the other thing I'm doing, I'm just taking the front panel off because I want to have a look and see if I mount the control box here, because it has RPM readout as well, and then maybe I don't need this and I can neatly set it into here. But first of all, we need to see what's behind here. Oh, the other thing it's got on is the potentiometer for the speed control that goes into the inverter, which is down here. Alright. So what have we got? Okay, so on this plate at the bottom, we've got the speed control. Looks like we've got maybe voltage and signal. We've got an earth connection, and then there's a potentiometer. 4.7k for that one. And then wasn't expecting that. It's like a power supply. Okay, so it looks like I've got a power supply in here, so we've got our mains coming in over there through the transformer, and then that's getting rectified down, presumably down to the DC through here, because that feeds into this sensor, so maybe that's dropping it to 5 or 12 volts. And then this cable here is just straight from the potentiometer that goes straight. Oh, that is the spindle that turns. It's not a sleeve. Yes, move this one. This is the speed sensor. I'll show you that in a minute. But it looks like just there, it's been rubbing because these wires just pass underneath it and just sit wherever. Luckily, the mains ones are a lot lower, just by chance really. But that one, which is the potentiometer, is starting to rub through, which should be interesting. Well, they didn't tie that off somewhere. That's really not good. Okay, well, we'll look at that in a bit, and then the other one, obviously, that's the sensor that comes through there, down to there, and yeah, ultimately to there. So this is getting power and that sensor, so if I don't need this and I can use this space, obviously I've got to retain some kind of earth feature if I need to encroach on that a little bit, but that's okay. And I mean, is that all that power supply is just to run this? I thought the inverters provided a 10 volt signal at least. Surely that would have been a better way to do it, but okay, that's what they've done. Alright, so well, that's what we've got. I can go away and think about if I want to use that space, and if so, how. Do I remake this plate? It'd be nice to use this. It's got all the branding and all the indicators on it and things, even if some of them may no longer. No, they'll still apply, won't they? Alright, anyway, that's what we've got there. Okay, so looking around the back of the machine for the mechanical bits that I've got to sort out, I've taken the banjo off here and the gears, and we've just got a shaft here with a keyway. It's just on the back. You can't quite see that. So I've got to make an interface that goes on there, so probably some kind of tooth belt system that goes on there that the stepper or the servo drives. So that's that bit. In terms of where I put that stepper or servo, James machined a pocket out of here and put it in here. Now the problem on my machine is directly behind here there's a fan that goes to the inverter, so there's no space to put it in there. It looks like it might go in here if I trim these threads back, which are the bolt mounting for the main lathe, onto the bench, but that would mean dismantling this if I ever move it, but you know, how likely is that? So I don't know, it might fit in there. It looks a bit small. If not, I'm not sure what my options are. I mean, I could cut a hole in here. It's pretty thick, because if I'm not using the power supply on the inside, there is space, but we do need the stiffness for this bearing, so I'm a bit reluctant to do that. I don't want to cut a big hole right next to the bearing pocket there. And then the other thing we've got to make space for is the encoder that's got to read off the main spindle. I think James put his about here. And then I've got to find a way to drive that, either remachine a pulley that's got a V in it, so I can run a V to that. Maybe come off the tooth gear that's already here that I'm not using, that would normally feed by the banjo. Some thinking to do, I think, to see how I can make it work for my application. So I think we'll finish off there with everything in pieces. As I usually like to start my projects, I need to go away and have a think about how I'm going to arrange everything. I hope you enjoyed this little introductory video just from working out exactly what I'm going to do to get this electronic lead screw to work. Obviously, you know, this is not a fit and forget kit. You've got to custom adapt it to your particular installation, but most of the hard work's already been done. So I've got a little bit of thinking to do. Hope you've enjoyed. If you've done a conversion, especially with James's, and you've had some experiences, do let me know. If you've done a video, post a link to that, would be even also good. Yeah, I think that's it for today. So hope you've enjoyed, and see you next time.